So we got that coding forms a salt. Okay, CH C18 H22. When this reacts with hydrochloric acid form this salt, Cl. Now, if you remember from before, when you have a salt, you have the cation of a base, because this is acting as a base, C18H22, NO3, and it's accepting a proton. Do you see? 21, sorry. It's accepting a proton. So this would be the cation of a weak base, which is this one, right? And this Cl would be the anion. We're going to see it in a little bit. We haven't done those questions. And this is why. That's true. If you look at this, when you got a salt, okay, the salt is formed by a strong, for example, let me put this example. The NH4 is the conjugate acid of a weak base, and Cl minus is the anion of the HCl, a strong acid. So when you got a conjugate acid of a weak base, which is the case here, that conjugate acid is going to react with water to form hydronium. This one, right, doesn't react because it's a very weak conjugate base that comes from a strong acid. And I'll explain a little bit more, but this is the case. This is the conjugate acid of a weak base. So this is going to react with water. This one, no, because it's from hydrochloric acid. This is going to react with water to form hydronium. So yeah, it's gonna give C18 back the base, like here, the coding 21 NO3 plus A30 plus. So it's going to be an acidic solution. The salt in water is going to be an acidic solution because this one is not going to react the Cl minus. So you got here that the Kb for the chlorine is equal to minus 10. And let me do it real quick, something here. Because we're going to need the IC, the ice. So here, let me do the Kb here. pKb is equal to 580. Kb would be equal to 10 to the minus 5.80. I don't know, remember, we have been doing this. So Kb would be equal to 1.6 times 10 to the negative 6. Okay, so now we're going to do the ICE for this. What is the problem asking? It's asking for the pH. And the hydrogen concentration comes from this, from the reaction of the strong conjugate acid of this base with water. So we have, this is the concentration initial, okay, because it comes from the coating of the coating, right? And here you got, of course, 0 and 0. So the change would be minus x. X and x, the same thing. And this would be 0.033 minus x. Directly. X and x. So the KB would be, like I said, given 1.6. Remember, the coating is a base, but we want the Ka because this is the reaction of the conjugate acid. So remember, this is a conjugate acid, so we need the Ka. But we know that the Ka is 1.0 by 10 to the minus 14 kW divided by Kb. 1.6 times 10 to the negative 6. So the Ka would be equal to 6.2 times 10 to the negative 9. Now again, this expression of the Ka to find out the concentration of X. And the concentration, X would be equal to the concentration of hydronium. So from there we can get the pH. 6.2 times 10 to the negative 9 equals X to the square, 0.033 minus X. As this is minus 9, yeah, we can drop this. Again, let me explain. This is a weak base, okay? The coating, when it reacts with, it says reacts with HCl, you form a salt, okay? And this is the salt. Now, like I said, when you got the salt of a weak base, this is the conjugate acid of a weak base, combined with the conjugate base of a strong acid, this is very weak, so it's not going to react with water. But this is going to react with water, and the reaction would be this one, producing hydronium. And so they're asking for the pH. Where are we going to get it? We're going to get, because the water also produces hydronium, but it's basically, we're gonna only use the one that comes from here, okay? Because that's what we've been doing when we have an acid. So this would be, this is important what I'm going to say. When you have an acid, you ignore the concentration of the acid, of the H3O coming from the water. And when you have a base, you ignore the hydronium coming, the hydroxide coming from the water. Hydronium, acid, hydroxide is for base. So you got x squared is equal to 6.2, I flip it, by 10 to the negative 9 multiplied by 0.033. That gives me x equals the square root of this, that it's 2.06 times 10 to the negative 10. And dx, which is the concentration of hydronium, That's correct, right? Equals 1.43 times 10 to the negative 5. Here you have it. You see? The hydronium concentration. So the pH would be equal to 4.85. It's not a difficult problem. The only thing is the salts. That we're going to do some exercise now with that, which is 29. Now, again, let me explain the acid, the salts, what happens with the salts, and how you're going to see it. Okay, this has exception. I don't like these problems from the Connect, and I'll tell you why. Because, okay, let's go first with the ones that yield neutral solutions. Where is it coming? A cation of a strong base doesn't react with water, and an anion of a strong acid is also very weak and doesn't react. So when in an aqueous solution, this salt doesn't produce hydronium or OH or hydroxide, so it's neutral. Remember, if you don't have excess of hydronium, a concentration of hydronium greater than the concentration of OH, is neutral. So in this one is neutral. Now let's look at the other salts. Here you got the conjugate base of a weak acid. It makes it a strong base. And this again is the cation of a strong base, which is not going to react. But here is going to be the conjugate base plus water is going to produce OH negative. You see, let's go back to the acid and produces hydroxide. So these salts use a basic solution. This one, the same thing. NH4 is the cation. Well, the same thing. No, here is a weakly basic solution. Salts of weakly acidic cations and weakly basic anions. Okay, produces a weakly acidic cation or a weakly basic anion, but it's going to depend on this. You see, if both are weak, it's going to depend on the Ka and Kb of each one. That's what happened, because in this one, here, this is a conjugated acid of a weak base. So it's going to produce a hydrogen in water. And this is a conjugate base of a weak acid. It's going to produce OH. But which one, which type of solution? A weakly acidic solution or a weakly base? Well, it's going to depend on the Ka of NH4 as a conjugate acid and the Kb of the CN. Okay, so as this is the Ka of NH4 is equal to the Kw, as this is the conjugate acid of a weak base, is Kw over Kb of ammonia, gives me this. Kb of Cn would be Kw over the Ka of ACN, gives me 1. Which one is going to be the K, since the Kb, okay, of Cn minus is greater than the 1 Ka of NH4, is a stronger base than NH4 is an acid, a solution of NH4Cl will be basic. It depends on the Ka and Kb of both conjugate. The conjugate acid, the Ka of the conjugate acid, or the Kb of conjugate base. So both of them, like I said, are going to react with water. It depends which one is greater. If Kb is greater, like this case, so it's going to be this reaction. And it's going to be a weakly basic solution. Okay, so now in this exercise is really a pain because here on this one, not too bad. This is like the case we had now. CH3, NH3 is the conjugate acid of CH3, NH2 of a weak base, which makes it a strong. And Cl is a weak conjugate acid because it's the conjugate, a weak conjugate base because it's the weak, is the conjugate base of a strong acid. Remember, it's the opposite. So this becomes, this is not going to react, so this becomes this CH3, NH3 plus water. It gives me, okay, CH3, NH2 plus H3O plus. By the way, this is plus here. So this is going to be an acidic solution. This one, this ClO4, right? This is a conjugate acid. The cation on a strong base, KOH, is a strong base and is soluble in water. And this would be the conjugate base of a strong acid, which makes it a weak conjugate base. And it's like the example I gave you on here, on the PowerPoint. It's up. Produces a neutral solution. So this is neutral. Now here it gets more complicated because this is the weak, the strong conjugate base, of a weak acid. If you have a weak acid, the conjugate base is stronger. But here, this is not the cation of cobalt, OH. Cobalt 2 OH. This is not a strong base because it's not soluble in water. So basically what it's going to be, okay, this is going to react and it's going to form a weakly acidic solution. That's when I said that this is a pain. The 30 is basically the same. You have to be careful when you see a cation of a strong base like this, if this K is soluble on OH. And basically looking at the, I have it here, at the solubility, that maybe you remember it by memory, salts with the, for OH of the 1A majority, especially Na and K plus, are soluble. 2A, these ones are soluble, the rest of the OH are not soluble. So let's go now to the 31. And 31 is a long way because it's again quadratic equation. But let's hurry up. Okay, so we got acetic acid. You have two ways of seeing acetic acid represented. It's like this, which is the hydrogen. That's how the inorganic chemists like to represent it. Or CH3COOH plus the water. I'm writing the ionization. Equals A3O plus the conjugate base, acetate. Okay, now you got here that you had to find all this. Okay, they give you already the Ka. So this I C E, yeah, we had to do it. And then this is going to be 0.280. We had to do the quadratic equation because I already proved, because this 0.280 is a big concentration. Maybe we don't have to do it. Let me check it out anyway. Let's do it without dropping the x. So I'm talking about the quadratic equation of dropping the x. So the change would be minus x. Oh, bingo. Plus x plus x. And this would be 0.280, because this is big, minus x, x, and x. So this is going to be Ka, and let's put the value, is 1.8 times 10 to the negative 5. So 1.8 times 10 to the negative 5 equals x to the square multiplied by 0.280 minus x. Let's drop it to see if then we'll double check if it was okay to drop it. 1.8 times 10 to the negative 5 multiplied by 0.280 equals x to the square. So x is equal to the square root of this. And this is gonna be, oh no, I didn't drop it, right. And this is gonna be the square root of 5. I dropped it on the, I didn't do the quadratic. 5.04 by 10 to the negative 6. Okay? Yeah, but I drop it because this is negative 5 and this is a big concentration. If it was 0.002, then we cannot drop it. So this is going to be 2.24 times 10 to the negative 3. This is the value of x. Let's double check anyway. By dividing 2.24 by times 10 to the negative 3, you can see it already. 0.280, but let's do it by 100 equals, I don't remember, 3 divided by 100. Oh yeah, 0.8% is much smaller than 5%. Okay, we got it. So now find the hydronium. You know hydronium would be, this is an acid, so hydronium directly is the equal, the X is hydronium, and they're asking for that. Ca3COO, the concentration of acetate. The problem is asking for all this. Equals 2.24, and it's 3 significant figures. Negative 23 molar. Yeah, they're asking for all of this. Oh. And POH too. And this is, yeah. And then you have that the concentration no, now we have to do the POH and the pH. So the pH would be the minus the log of the 2.24 times 10 to the negative 3. And as this is an acid solution, the pOH comes from the water, the ionization, auto-ionization of water. And the pH would be 2.65. You see? There's two ways, you know how? By subtracting the 14. I think that's going to be the shortest one. pOH plus pH gives me 14. So it's 14 minus 2.65 equals the pOH equals 11.35. Now the concentration of OH comes from the water. You see, we had to do both things. Equals 1.0 by 10 to the minus 14. And it's going to be 2.24 times 10 to the negative 3. So the concentration of OH would be equal, negative, of hydroxide would be equal to 4.46 times 10 to the negative 12. And as this connect is unpredictable, I think on this exercise you have to put the 2 decimals. I remember. If not, I would have put 1 decimal, 4.5. But no. And finally, this was 31. And the last one, finally, okay, is the same but with KB. If you want, I can do it real quick. It's identical because they're asking for the same thing and the pH and pOH, but this time is NH3. Well, that I worked so already, I've been working so hard, so many videos, doesn't matter. 2 minutes more. Plus H2O gives me NH4 plus OH negative. And we go the opposite way. Again, ICE, ice. And this is going to be 0 point, is given, the initial concentration of ammonia of the base is given. This would be minus X plus X plus X. So 0.150 minus X, X and X. And you know what I do this, all this, because you probably, for the homework, you probably say, okay, the ammonia is, the Kb for ammonia is 1.8 10 to the negative 5. If you notice, it's the same as the Ka for acetic acid. And you can do it directly, okay, without doing the IC, because you know by memory already this. But I'm doing it on purpose to remind you that if when you're on the test, you have to do it. Okay, when you write your calculations and you show me your work. And it's 0.150 minus X. Again, we can drop this, okay, with a smaller one. So X would be the square root of 1.8 times 10 to the negative 5 multiplied by 0.150. So if you multiply this and get the square root, X would be 1.643 times 10 to the negative 3. And molar. And connect doesn't have it with exponent, so you have to, the concentration of OH is equal to 0.016. No, I need another 0. See, I was going to do this. Okay, 0.016 molar. And so the POH would be the minus the log of this of 0.0016. So POH would be equal to smaller. Remember, you have a base, so the POH should be small. And then, I hope you remember this. POH is smaller because you have a base, and pH should be higher. And when you got an acid, pH is smaller, POH is high. So let's find the concentration of H3O. By the way, here I did already the 5%. What do you do it to check if I did this, if I drop the X? Remember, it's the X divided by 150 multiplied by 100. Okay, so the concentration of ammonia, of hydronium, is going to be 1.0, of course, kW 10 to the negative 14 divided by 0. The hydroxide 164. I'm going to use the 366. And this is going to be 6.098 times 10 to the negative 12. And this is going to be 6.10, 1 by 10 to the negative 12. Did you notice that I rounded to 2 here and 2 here? Well, that's what you need to put it in with 2 sig figs. If not, it's going to mark it wrong. Both values of this was 2 decimal, of course, POH and pH. But the concentration of OH, you have to put it with 2.16. And the concentration of H3O, because they're considering the 1.8 by 10 to the minus negative 3, which is a KB, as 2 significant figures. So we got here, okay, 6.1, you enter that value. And the pH, of course, is the minus log of the concentration of hydronium, and is 11.22. It gives you in the, well, you're going to get different values, and you need to make sure. Let's look at something here that when I was doing here, I thought, yes, I forgot this. What did I forget here? The M, the unit, imagine. Because I'm working with a lot of, yeah, here is right. I'm working with a lot of non-unit, using the X without unit, and then when I do it, don't forget to do this, to put the M here. And I'm done in 32 problems, and they're all at 7:57, 8 o'clock, how I promised, they're all here.